chapter 8 in the notes, Bezier curves. We're also going to be looking at B-splines as well, which are a sort of a way in which we can join multiple Bezier curves up. Okay, all right, guys, I know you come in late. Excuse me. I've started the lecture, so I know you come in late. You don't start talking now. Okay, well, Bezier curves are simply polynomial functions. Okay, so we're just going to do a quick recap of polynomial functions. This should be familiar. So we'll go back to GCSE and A-level work. Okay, a polynomial is simply a sum of variables raised to powers and multiplied by coefficients. So, for example, a quadratic function is a polynomial function. So x is your variable. You have different powers of x. You multiply x by some number. When you add them together, you get a polynomial function. Okay, well, we refer to the degree. Well, the modern parlance seems to be degree. I've always used order, but they seem to be interchangeable. The degree of a polynomial is the highest power of the variables. Okay, so for example, at the bottom here, we have what we call a fourth degree polynomial or a fourth order polynomial, because the highest power of x is 4. And you should be familiar with these. We have linear polynomials, which we have quadratic polynomials, highest power of x is 2. Cubic, highest power of x is 3. And quartic, before, quintic 5, septic 6, etc., etc. Okay, so this is what we're going to be doing today. We're going to be looking at polynomials to draw nice, smooth curves. Oops, wrong computer. Okay, one thing I want you to realise is the higher degree of the polynomial, the more twists and turns it can take when we graph it. So if we have a look at this linear polynomial on the top left, that's a straight line. So linear, so the highest power of x is 1, we simply have a straight line. In the top right, we have an example of a quadratic. That's either a cup or a cap shape. So that has one change of direction. In other words, one local maxima or minima. A cubic can have 2 changes of direction, kind of like an S sort of on its side. A quartic can have 3 changes of direction. A quintic would have 4, etc., etc. So the number of sort of changes of direction for when we graph these polynomials is 1 less than the degree of that polynomial. Okay, so the higher order, the more sort of wiggly we can make the line. Lower order, the less wiggly, in other words. Okay, Bezier curves use polynomial functions, but they also use parametric equations. Not a lot to parametric equations. We've actually been dealing with them all of this year. The vector equation of a line is a parametric equation where t is a parameter. So those of you doing the clipping assignment, you have to calculate t. Okay, that's your parameter. Okay, so if we have, for example, an equation of a straight line, okay, a point on our line would have an x and y coordinate. And the x and y coordinate can depend on that parameter t. Okay, so let's say we have a line joining points x0, y0, and x1, y1. Okay, so those are 2 endpoints of our line. T is a parameter, and that parameter is in the range 0 to 1. Okay, so t can take on any value as long as it's between 0 and 1. And we can calculate coordinates of points on that line, x and y, based on that parameter t. And these are the parametric equations of a straight line. So 1 minus t times your first x coordinate plus t times your second x coordinate. Okay. And that'll give you points along this line. Okay, so there's our line. That's a parametric equation of the straight line. So p is going to be my coordinates of the point at the parameter t, at p0 and p1 are my start and end points on this line. So when t is equal to 0, 1 minus t would be 1, and t times p1 will be 0. So when t is equal to 0, p would equal to p0. When t is equal to 0.25, okay, we have 1 minus 0.25, which is 0.75, plus 0.25 times p1. So we've got 0.75 times the first coordinate, plus 0.25 times the second coordinate. Okay, so you're a quarter of the way along this straight line here. When t is equal to a half, you're halfway along. When t is equal to 3/4, you're 3/4 of the way along, etc. And finally, when t is equal to 1, well, 1 minus t would be 0, and then you just have 1 lots of p1. So when t is equal to 1, you're actually at p1. Okay, so t has a parameter in the range 0 to 1, and that determines how far along that line you are. So the points of coordinates of a point along that line, how far along. If you can understand that, I saw there is really 2 Bezier curves. Okay, we've got another bit of algebra thrown in, but that's the sort of key to a Bezier curve. Now, again, are there any? I think I asked this question before. There are no French speakers in the house. Okay, because I'm probably mispronouncing his name. It's Bézier or something like that, but I say Bezier. So a Bezier curve is a parametric curve that is used to draw curved lines, or smooth curved lines. And it's named after a guy called Pierre Bézier, who was designing cars for Renault. So car manufacturers, back in the olden times, it's sort of, cars used to be a bit more sort of square and blockier than they are now. And over the years, car manufacturers want to make them nice and rounded, partly because of aesthetics, partly because of aerodynamics. But if you look at modern cars, they're all sort of nice and rounded and things like that. So he was working for Renault, and he was developing algorithms to actually define a curved line. And he came up with Bezier curves. So coincidentally enough, there was another chap who was working for Citroën at the time, called de Casteljau, who actually invented this 3 years earlier. But we know him as Bezier curves. Don't know why. Just de Casteljau just got unlucky, I suppose. Okay, so it's actually invented by Paul de Casteljau 3 years earlier, but we know them as Bezier curves. And these have been used in computer-aided design software, 3D modeling, typefaces especially. When you look at a font on the screen, that's drawn using Bezier curves. Okay. We could have different degrees of Bezier curves. Okay, so an n-degree Bezier curve is defined by what we call control points. So we need 1 more control points than the degree of the Bezier curve. So if we've got a quadratic curve, that's got a degree 2, so we need 3 points to define it. If you want to make translations, if you want to scale, rotate, move, anything like that, anything which we've been doing, they can easily be applied to the control points. So for example, if we have a quadratic curve, that's defined by just 3 points. We can translate those 3 points, or scale them or rotate them, just on 3 points. So it's quite simple. And then we apply the Bezier to those translated points. So we don't have to do translate the whole curve. You only have to translate the control points. Now here's an example of a typeface. This was actually the Bezier curve assignment from a couple of years ago. All I did there is I printed out the letter S using the Times New Roman font, sort of large printout of it. And I sort of tried to mimic it using Bezier curves in MATLAB. Okay, so there's multiple curves sort of joining this. Okay, so there may be a curve around here, and then another one around here, another one up there. Okay, so that's my attempt at drawing an S using Bezier curves. you notice what you can then do is I scaled down the control points. So these sort of red circles you can see here, these are control points. I scaled them down and then calculated the Bezier curve using the scaled down points. So you can see it's easy to scale up and down the font in that way. Okay, so that's one of the applications of Bezier curves. Okay, so let's have a look at derivation of a quadratic curve. Well, I mentioned that degree n Bezier curve means n plus 1 control points, so therefore we have 3 control points. Now it's convention to start your numbering at 0. So the 3 control points are P0, P1, and P2. Now what we're going to do is, those are the 3 control points, and we're going to define Q0 and Q1. Okay, these are kind of intermediate control points. Now these are going to, Q0 is going to be on the line joining P0 to P1, and Q1 is going to be on the line joining P1 to P2. Now when t is equal to 0, using the parametric equation of a straight line, Q0 is at P0, Q1 is at P1. But if I increase the value of t to be 0.1, okay, Q0 is now 1/10 of a way along the line joining P0 to P1, and Q1 is 1/10 of the way along the line joining P1 to P2. Okay, so that gives me Q0, Q1. And what I've also done is 1/10 of the way along the line joining Q0 to Q1, which is the blue line, I put a dot. Then I'm going to do the same for t equals 0.2. Okay, so we'll go 2/10 of the way, or 1/5 of the way along each line. So Q0 moves up to here, Q1 moves down to here, and I put a dot 1/5 of the way along the blue line. And if I keep going, okay, you can see Q0 moves closer to P1, Q1 moves closer to P2, and I'm drawing that black dot along Q0 to Q1. So just sort of show that again, as you can see. So those black dots are on my Bezier curves. That's similar to this activity which we did at the start. Okay, and then if I join a line through those dots, that's your smooth curve. That's all there is to it. That's a quadratic Bezier curve. But the problem is with this approach is we don't want to have to draw lines and sort of measure how far along that line we are. We want to be able to define this algebraically. Okay, so the challenge is we want to come up with an algebraic expression to draw that Bezier curve. Okay, so Q0 and Q1 are the points on the lines P0 to P1 and P1 to P2. So therefore, using the parametric equation of a straight line, we have these 2 expressions. So this is where Q0 is, that's where Q1 is. Now, I'm going to define CT as my point on my curve. So CT is going to be the point on my Bezier curve. Now that's on the line between Q0 and Q1. So using the parametric equation of a straight line, we have 1 minus t times Q0 plus t times Q1. And what you could do here is, instead of Q0, we can substitute this top expression in. And instead of Q1, we can substitute this bottom expression in. Okay, so if we combine those 2, do a bit of algebra, rearrangement, we get this expression. So here we have a parametric expression only involving the control points P0, P1, and P2. Notice the power of t, the highest power of t is 2, which means this is a quadratic polynomial. So this is my quadratic Bezier curve. Okay, so that's how we derive Bezier curves. Now, well, that's quite easy for quadratic, but as we get to sort of cubic and quartic, it gets the algebra gets quite complicated. And so, Casteljau, who was actually the person who originally derived Bezier curves, he came up with an algorithm called Casteljau's algorithm. And what we do is we introduce a notation where Pij, so subscript ij, denote the control points. So if j is 0, that's your initial control point. When j is 1, you have your intermediate control points, which is q. When j is 2, you have your next level control points, say r. Okay, so the j denotes sort of what level we're at. When j is 0, we're at the original control points. Okay, so Pi0 are the original control points, P0, P1, P2. Pi1 denotes Q0 and Q1. P02, well, that's the point on the Bezier curve. That's what we want to find. We want to find P02. Okay, and the algorithm is like this. Okay, so P subscript ij is essentially the parametric equation of a straight line. 1 minus t times pi j minus 1 plus t times pi plus 1 j minus 1. So that's quite tricky to sort of visualize. It's like, oh, you've got lots of i's, lots of j's, you've got minus 1s, you've got plus 1s. So to Casteljau sort of suggested this, what we call a triangular sort of algorithm. Okay, so there's your Pij minus 1. So there's your Pij. That's what you want to calculate. That's equal to a combination of this value, so j minus 1 because we've gone 1 to the left, and the value below it. Okay, so each point is going to be a combination of 2. This horizontal arrow denotes the I minus 1, so we multiply this point by I minus 1, and the diagonal arrow we multiply by t. Sorry, 1 minus t. So the horizontal arrow denotes the 1 minus t coefficient, the diagonal arrow denotes the t coefficient. Okay, that looks quite complicated. It's like with many things, as soon as we start to have a look at an example, it gets a bit clearer. Okay, so this is our quadratic Bezier curve. We've already derived this, but we're going to have a look at it using Casteljau's algorithm. Okay, well, instead of P0, I'm going to label this P00, because this is the second number j. When that's 0, we've got our original control point. Okay, and therefore there's P1, so that's P10, and therefore there's P2, P20. Now, what I had labeled as Q0 and Q1. I'm now labeling P01 and P11. Okay, and the point on our curve is P02. Okay. Oops. Okay, so we want to find P02. Well, P02 is a combination of P01 and P11. Okay, so remember these are Q0 and Q1. So the horizontal arrow denotes multiplied by 1 minus t. The diagonal arrow denotes multiplied by t. Well, in turn, each of these P01 and P11 are also combinations of two points in the level before. Okay, so P01 is a combination of P00 and P10, and P11 is a combination of P10 and P20. Okay, so we could work through to derive our Bezier curve. So P02, using Casteljau's algorithm, is this. Okay, so just a combination of the blue. I've color-coded them blue here. Okay, well, each of those blue ones is a combination of the red ones. So here, instead of having P01, I've replaced it with this square bracket. Okay, so P01 is 1 minus T times P00 plus T times P10. Okay, and likewise, this P11, which is this one here, is a combination of P10 and P20. Okay. If I multiply, well, do a bit of algebra. So what we got here, 1 minus T times 1 minus T gives us 1 minus T squared. I have 1 minus T times T. And I also have a 1 minus T times T there for the same point. That gives me 2 of them. And finally, we have T, T there times T there, which gives me T squared. Okay, so that's the quadratic Bezier curve. What about a cubic? It gets a bit more complicated now. Now, a cubic is defined by 4 control points, 3 plus 1. Okay, so your original ones are in red. So I've got P00 all the way around to P30. So the ones in red are the original control points. The ones in blue are part way along the ones in red. The ones in green are part way along the ones in blue. And finally, the point on our Bezier curve is part way between the green ones. So there's an extra step here, there's an extra level. That's a cubic. Okay, so we can do the same thing. Okay, you see there's a pattern, that triangular scheme. So your P03 is what you're trying to calculate. And that's a combination of the green ones. Each green one is a combination of 2 blue ones. Each blue one is a combination of 2 red ones. So it's not difficult, it just requires quite a bit of work. Okay, so doing exactly the same. So we have, this is our P03 is our Bezier curve. That's a combination of the green ones, P02 and P12. Now P12 is a combination of the blue ones. So I've just replaced the green ones with these square brackets. Now, I've got to do this again because each blue one is a combination of 2 red ones. Okay, so it gets quite lengthy. You're looking at a bit of algebra here. Okay, so what we have here is we have some expression involving P11, P10, P20, and P30. Okay, which were our original control points. Okay, do a bit of algebra, simplify down, and we get this expression. And this is the cubic Bezier curve. Okay, so that's P03 is the point on the Bezier curve, and you can see the highest power of T is 3, so we have a cubic parametric function. Now, we don't actually derive Bezier curves in that way. Okay, Bernstein sort of noticed there was a pattern emerging. Okay, if you have a look at this bottom line here, okay, we have 1 minus t cubed, we have 3t, 1 minus t squared, 3t squared, 1 minus t, and then t cubed. Okay, have a look at that. Have a look at the quadratic one. We have 1 minus t squared plus 2t, 1 minus t plus t squared. There's a pattern there. Okay, so we can actually use that pattern to derive our Bezier curves. Okay, and this pattern essentially uses what we call Bernstein polynomials. Okay, so we can calculate an n-degree Bezier curve. So if I wanted a 10th degree Bezier curve, which probably I wouldn't really want one, but if you did, it's easily calculated. And the Bezier curve is simply a sum of your control points multiplied by a Bernstein polynomial. Now these Bernstein polynomials, bin, n is a degree of your Bezier curve, I is just the sum index there. Okay. What it is this is the what we call the binomial coefficient. This isn't a matrix. It looks like a matrix, but it isn't. It's actually we're choosing I items from n items. We say n choose I. It's what we call the binomial coefficient. You might have seen it in probability. Okay, so we've got n choose I, t to the power I, 1 minus t to the power n minus I. And that's a Bernstein polynomial. Okay, just a quick note on the binomial coefficient. How do we calculate it? Well, binomial coefficients, one way of defining them is using this. Because we're only dealing with fairly small numbers, okay, we actually rarely go above 4th degree or even 5th degree. Okay, it's probably easier to use Pascal's triangle. I take it you've all seen Pascal's triangle before. We have ones on the outside. Every number is the sum of the two numbers above it. So that's 4 there, 1 plus 3, that's 6, 3 plus 3, etc. Now this gives us the binomial coefficient. So for example, 4 choose 0 would be 1, 4 choose 1 would be 4, 4 choose 2 would be 6, etc. So you can just read across. So 3 choose 1 would be 3. Just an easy way of doing it. Okay. So look, going back to the Bernstein polynomials, if we had a cubic Bezier, so n would be 3, and we need to, we've got 4 Bernstein polynomials, I is 0, 1, 2, and 3. Okay, so when I is 0, we have 3 choose 0, t to the power 0, 1 minus t to the power 3 minus 1. Sorry, 3 minus 0. Okay, well, 3 choose 0 is going to be 1. Okay, that's that number there. Anything raised to the power 0 is 1. So that t to the power 0 disappears. That's just going to be 1. 1 minus t to the power 3 minus 0 is obviously 3. So that Bernstein polynomial is 1 minus t to the power 3. When I is 1, we have 3 choose 1, which is 3. T to the power 1, which gives us that t. 1 minus t to the power 3 minus 1, which gives us 1 minus t squared. When I is 2, we have 3 choose 2, which is also 3. T squared, that's t to the power I, there's your I. 1 minus t to the power 3 minus 2. And finally, when I is 3, 3 choose 3 is 1. T to the power 3, 1 minus t to the power 0. Okay, so 4 Bernstein polynomials, not too difficult. And these are multiplied by our control points to define our Bezier curve. Okay, so that's another way of deriving them, probably the easiest way. We don't have to go through lots and lots of algebra. All we have to do is derive them separately and then multiply them by the control points. Okay, and here are the Bernstein polynomials. This is for a quadratic, so we've got 3. Along the bottom, horizontal axis, that's my t-axis, so that goes between 0 and 1. The vertical axis is the value of that Bernstein polynomial for different values of t. And you notice it max out at 1. Okay, so this blue one here, that corresponds to the Bernstein polynomial which is multiplied by the first control point. The red one is multiplied by the second control point, the green one by the third. So what does this mean? Well, in our Bezier curve, let's say when t is small, let's say t is somewhere about 0.1. What this means is most of the value of the Bezier curve is influenced by the first control point, p0, and then some of it is multiplied by this, some of it sort of behavior comes from the second control point, and a tiny bit comes from the third. So these Bernstein polynomials say how much control do these control points have over the Bezier curve at that point. For example, when t is equal to 1/2, it's the middle control point which has most effect, and P0 and P2 have equal amount of effect. As t gets larger, it's the last control point which has more of the effect, followed by the second one, or the middle one, followed by the first one. So as we sort of slide up and down the t, you can see which control point has most effect on that Bezier curve at that point. Another thing to note about this is if I was to add up these values, so I'm adding up the green, the blue, and the red line, it always sums up to 1. So if I was to add these, it always sum up to 1. That's for a quadratic. Same thing for a cubic. In this case, we've got 4 of them. Could have done quintic, but yeah, gets quite fairly similar. So that's sort of the behavior of the Bernstein polynomials. Okay, so that's derivation of Bezier curves. How do we actually calculate them? Well, in practice, we use matrices. So Bezier curves are pre-calculated. So we don't sort of derive them every time we want to use a cubic. We pre-calculate matrices for a cubic or for a quadratic, and then use them to calculate our points. So here we have a matrix equation. CT is my curve. P0 to Pn. Now these are my control points. Okay, so in 2D space, this will be a 2 by n array, or 2 by n matrix. Okay, so imagine these are all column vectors. P0, so you might have x and y, P1, x and y, etc. M is going to be an n+1 by n+1 square matrix, depending on what method or what degree Bezier curve you have. And then here we have a vector of t values. Okay, so this is an n+1 column vector of t values. So at the top we have t to the power n. So if that was a cubic, it would be t to the power 3. And then going down, we subtract 1 from the power, all the way down until we get to 1 at the bottom. Okay. Now, how do we calculate that m? Okay, so if we have a look at the quadratic Bezier curve, I've written it in the form, I've multiplied out the brackets. Okay, so you have t squared minus 2t plus 1 is multiplied by p0. Okay, so that corresponds to this top row. Okay, so 1 times t squared minus 2 times t plus 1. Okay. P1 is multiplied by minus 2t squared plus 2t. So that's minus 2t squared plus 2t. And finally, we just got t squared times p2. Okay, so this square matrix here, that's our m. That's the same for every quadratic Bezier curve. And if I do similar for a cubic, we have a 4 by 4. And again, that's the same for every cubic Bezier curve. Now your assignment 11 is using MATLAB to calculate a cubic Bezier. Okay, so you'll be using this matrix equation. Keep using the wrong computer. Okay, so that's, I've done it for a quadratic. I'm not going to do it for a cubic because that's your assignment. But you can see it's quite simple, really. Only 3 lines of code. So this function, if I'm given the control points p, and that's going to be a 2 by n. In this case, it's a quadratic, so that's going to be a 2 by 3 coordinate array. And t is going to be a vector of parameter values between 0 and 1. Define m. There's my m matrix, a 3 by 3. And then I define my column t vector. That was t squared, t, and t to the power 0. Well, that's just going to be 1 anyway. Note that with the t squared, I've got a dot before the power symbol because it's element by element. Then all you do to calculate the Bezier curve, c, which is the curve, is equal to p, which is your control points, times the matrix m, times your t vector. That's it. Dead easy. So that's the function. So In a minute, I'm going to show you that in action. Actually, I'll do that now. Okay, so I've preloaded the. Okay, so I've preloaded that in. So what I'm going to do is just draw some quadratic Bezier curves. For some reason that's. Oh. I don't know why that's zoomed in. I'm going to just start that again. For some reason, when it's because it's zoomed in on the when I've gone to the projector, it's okay. So, ooh, hang on, give me a. Oh, you swine, MATLAB. Anyway, I'm going to see if it works anyway. So if I click a point there, oh, something's appeared at the bottom. I'm not quite. Okay, something's gone a bit wrong. Yeah, it's probably when it's sort of it's boosted. It's yeah. Okay, that's gone a bit wrong. I'll come back to that. Okay, what I was trying to show you is something like this. Okay, so those are Bezier curves, which are generated. So these are cubic actually. So 4 control points. The blue line is a curve. The red sort of lines show you the control points. So as you can see, you have nice sort of smooth curve. Okay, you can make it go in on itself. You can actually make it twist back on itself. So that's the first control point. That one's the second. That one there's the third. And that one down here is the fourth. So you can see it actually, you can actually make it like a loop. And you can make a little wiggle, a little sort of zigzag. Okay. The higher the degree, the Bezier curve, the more sort of changes of direction it can take. Okay, well, properties of these. A Bezier curve will always begin at the first control point and end at the last control point. So when t is equal to 0, you're at P0. When t is equal to 1, you're at Ps. Okay. You can have a Bezier curve be in a straight line, but all of your control points must lie on that straight line. The start and end of a Bezier curve is tangential to the start and end section of the control polygon. So what does that mean? Well, here, this is my end. Let's say this is my end of the Bezier curve. This last, the line joining the penultimate to the last control point has the same gradient as the point at the end of the Bezier curve. Any Bezier curve can be split into 2 separate Bezier curves. And the Bezier curve is contained within its control polygon. So that means if I draw a polygon using the control points, this Bezier curve cannot go outside of that control polygon. Okay, it's called the convex hull property. That's useful in things like design. You know, if you're designing stuff, you don't want it. You know, you've got particular boundaries or particular constraints on dimensions. Okay, so that's Bezier curves. Your assignment for assignment 11 is, well, actually, if I bring it up. I don't want to show you the solutions. Sorry about that. Okay, as you know, it's all on Moodle. Solutions? No, I'm afraid not. Okay, so just want to talk through the just talk you through the assignment 11. And as I mentioned, it's not dependent on any prior or previous assignment. Oh, I didn't need to click on that. Sorry about this. This machine's a little bit clunky. Okay, let's zoom all the way down to the end. Okay, so this is assignment 11. So first question, write out a matrix equation that calculates the coordinate of the point on a cubic Bezier curve defined by 4 control points in the parameter t. I just showed you that on one of these slides. I'm not going to tell you which one. You can go and look for yourself. Okay, question 2. is a hand calculation. So I've given you 4 control points. What I want you to do is calculate the coordinates of the point on the Bezier curve corresponding to those values of t. Now, in a minute, we're going to do one of the activities for quadratic. It's very similar to the cubic. And part B, write the MATLAB program that plots that Bezier curve. And I want you to use about 100 values of the parameter t. Okay, so on the previous, one of the previous slides, there, that's for quadratic. I want you to do similar, but for cubic. Okay, question 3. What I want you to do is use Bezier curves to design or to try and draw the MMU logo. Okay, and it looks quite daunting when you look at it like that. But I'll show you the steps I used. Okay, so to start with, 3A is design, I've called it an arrowhead. Okay, that's drawn using 8 separate Bezier curves. Okay, so I've got one curve going from that point there around to there, and I've got another point going from that point up to there. Okay, and then similar on the other side. Notice there's a line of symmetry down the center. So once you've got those 2 curves, it's quite easy to find these 2 curves. Okay, so I want you to draw this arrowhead. The ones on the outside again are similar. So I've got a curve starting here and ending around about here. I've got another curve starting there and ending about there. And again, a line of symmetry. Okay, so that's the first thing I want you to do, is to be able to draw that arrowhead. Notice my axes, 0, 0 is around about the center of the arrowhead. Why have I got it in the center at 0, 0? What do you think? It's an object. Yep, this is an object. So if it's centered at 0, 0, it means I can translate it. Actually, I can rotate it and it will rotate about itself. And then I could translate it and move it somewhere. So the second bit is you have 6 of them. So once you've defined, or once you've drawn the first arrowhead, we just copy and paste that. Well, I say copy and paste that. We translate it and rotate it. Okay. Takes a bit of trial and error. I'm not going to lie. I didn't do this straight away. I had to sort of up it down a bit, twist it around a bit more, type thing. A bit trial and error. But eventually you'll have 6 of them in that sort of configuration. And you can see that's sort of starting to look a bit like the logo. And all I did to finish it off is I sort of filled in the background in blue, so all this bit around the outside. The outside arcs are filled in white, and the inside arcs again filled in blue. And then you can create a logo. Okay, so this is one application of Bezier curves. It's used in graphic design. Okay. So that's what I want you to do for assignment 11. I should say, and I may say this for a few assignments, but this one especially, questions 1 and 2 are quite easy, quite nice. So if you want a bit of a break from your other assignments, have a go at this one. Okay, so I'm actually going to show you how to do question 2A in a sec. Yeah, I'll start that in a sec. Okay, so they're Bezier curves. We can actually extend Bezier curves further to create what we call a Bezier surface. So rather than have a 2D line, we could have a 3D surface. So Bezier curves use a parameter value t, which is somewhere between 0 and 1. For a surface, we need 2 parameters. We call them u and v. These are just like t, these are in the range 0 to 1. Okay, so we have 1 for the x direction and 1 for the y direction. Bezier surfaces use Bezier curves in the x and y direction. We can have different degrees of curves for each direction, but in practice we tend to do the same for both, just for ease. Okay. So what we can say is we can have a Bezier surface of degree mn, where n is a degree of the Bezier curve in the x direction, and m is a degree of the curve in the y direction. But as I mentioned, m normally equals n, just for ease. Okay, so our control points this time take the form of matrices. So rather than having coordinates, what we need is an mn Bezier surface needs m plus 1 by n plus 1 matrices. So one for x, one for y, one for z. So remember, we've got 3 dimensions now. Okay, so these are our control points, or our coordinates of our control point. Okay, and all we do is we sum across and up some Bezier curves. This may look quite complicated, but what all this means is these are the x, y, and z coordinates of a point on our Bezier patch or Bezier surface. And what we do is we sum through all the x direction. So this sum for I equals 1 to m is summing multiple sort of Bezier curves in the x direction, and the outer sum is summing it in the y direction. And again, we use the same Bernstein polynomial. So here we've got a Bernstein polynomial in terms of u. Here we've got a Bernstein polynomial in terms of v. It's a lot easier than it sounds in practice. Okay, we can form this matrix equation. So this is just for the x coordinate, it's similar for y and z. Okay, so our x coordinate on our surface. Here we've got a row vector of u values. So remember we had the column vector of t. Well, here we've got a row vector of u values, starting with u to the power m. So m is the degree of the Bezier curve in the y direction. Okay, so go all the way down, we subtract 1 from the power of u until we get down to 1. Then we multiply it by a square matrix M, which is your Bezier curve matrix. Then that's multiplied by px, which is your matrix of x coordinates on the surface. Then it's multiplied by n, which is your Bezier curve in the y direction. And then it's multiplied by a similar column vector, but this time it's the parameter v's. Okay, so m and n, let's say we have degree 3, 3. So we've got third order Bezier curves in both x and y directions. Okay, so there's the m matrix, the third order Bezier. There's your u's, so you're going to have u cubed, u squared, u, and 1. In the middle, you have, this will be a 4 by 4 matrix of x coordinates, and then we've got v's on the end. So it's just a series of matrix multiplications. So that's the MATLAB. Okay, so there's my m, there's my u, so this is my u array, and there's my v array. Okay, so the inputs for this Bezier surface are px, py, pz, which are all matrices of coordinates in the control points, and u and v, which are your parameter values, an array between 0 and 1. Okay, and there we are at the bottom. To calculate the x, y, and z coordinates, it's u times n times px times n times v. And we do similar for y with py and z with pz. So that's the result. Okay, this is just a random, what I did is I just asked for a random numbers. Okay, so that's a 3D plot of control points, and it's just random in the z direction. So I've got x and y, and then some random element in the z direction. And what I've done there is I've applied a Bezier surface to that control point, and you can see it gives you a nice sort of smooth thing. So you can see if you're designing a car or something like that, you can have a nice sort of smooth bonnet just by using some control points. Okay. Those of you who've done assignment 8, is that the Teapot one? Okay, you've actually used these because the Teapot uses Bezier patches. So when you download the data for Newell's Teapot from the internet, that's what you get. You get the control points. It sort of looks like a teapot. You can make out the spout and handle, but it looks a bit angular and it looks a bit sort of pointy. So those are the control points So you can apply Bezier patches to the control points, and you get the teapot on the right. So that's Bezier patches. Okay, right, what I want you to do now is just turn over the page on this activity, and essentially this will help you with the assignment 11. Yeah. Why haven't you got one? I see. Where are they? Got a load of spares somewhere. Oh, you're lucky. How many do you need? Right, so hopefully your ears to prick up. This is going to help you with assignment 11. Okay, so I've given you 3 control points, P0, P1, P2. And I've also given you the matrix equation for the Bezier curve, quadratic. Okay, so what I want you to do is calculate the points on the quadratic Bezier curve corresponding to the following values. So I've given you 4 values of t. I want you to calculate that point. Okay. What I'm actually going to do first, which I'm asking you to do, is I'm going to just put on the control points on this axis. There's 1, 1, 7, 5. Is there. And 9, 3. Okay, so that's your control points. Right, so we're looking to start with when t is equal to 0.2. Okay, so what we have is, okay, we have our 3 control points here, P1, P2, P3. So our first control point has coordinates 1, 1. That makes up the first column. So the first column is the first control point. The second control point is 7, 5. That's my second column. And then we have 9, 3, which is the third column. So that's my control points. Then that's multiplied by the M matrix, which this is the same for any quadratic Bezier curve. And that's found using Casteljau's algorithm, etc. But once you've done that once, you never have to do it again. Okay, and finally we have our t vector. So we have t squared, then t, then 1. Okay, so when t is 0.2, that's going to be 0.04, isn't it? Just going to check. So 0.2 squared is 0.04, and t is just 0.2, and then 1. And we're just going to multiply those together. So I'm going to multiply the first 2 together to start with. So what we got 1 times 1 minus 14 is minus 13, plus 9 is minus 4. Okay, second one, minus 2 plus 14 is 12. Yeah. Now 1, 1. Okay, second row. What have we got? I've got 1 minus 10, so that's minus 9, plus 3, so it's minus 6. Minus 2 plus 10, that's 8, plus 0. And I just got 1, plus 0, plus 0. Okay, so I'm left with a 2 by 3 times a 3 by 1. So what am I going to do? What's the matrix going to result from that multiplication? 2 by 3 by 3 by 1? 2 by 1. That's 2 by 3, 3 by 1. The two outside numbers give you the what you're going to end up with. Okay, so I have to reach for a calculator here. Okay, so we've got minus 4 times 0.04. Okay, those two plus 12 times 0.2 plus 1. 3.24. Okay, and similar for the bottom row, minus 6 times 0.04 plus 8 times 0.2 plus 1, 2.36. Okay, so that's your point on your Bezier curve corresponding to t equals 0.2. Okay, so that's 3.24 and 2.36. So 3.24 is around about there. 2.36 is about that. It's about there. Okay, so that's for t equals 0.2. What about t equals 0.4? Well, when t equals 0.4, we're going to have the same first two matrices, aren't we? Because the only thing that changes is the third matrix. So these first two are going to be the same, so I might as well just write that one down. There's no point redoing that, because I know that's going to be the same for these control points for every value of t. What is 0.4 squared? 0.16? 4.4 is 1. Okay, C is when t is equal to 0.6. It's going to be the same first matrix, 0.36, 0.6, 1, and D is same first matrix. This time it's going to be 0.8 squared. Okay. Just 3 matrix multiplications to work out. As always, double check my working out. So now we've got 4 coordinates and points on our Bezier curve. Okay, so we can put them on to the axes. So 5.16, that here, 3.24, should be about there. 6.76 and 3.64. Right there. And finally 8.04 and 3.56. Going to do that there. And then what you can do is you can just try and draw a smoothish line through them. Smoother. I've done that there. Okay, so all this boils down to is just some few matrices multiplied together, and you've got your quadratic Bezier curve. Now you've got to do similar for the cubic. Somewhere in my notes is this square matrix, and for cubic you'll have a 2 by 4 matrix for your control points, and you'll have a 4 by 1 vector of your t values, t cubed, t squared, t, and 1. And you just do similar. That's how you do the assignment. Okay. Any questions regarding that work? Hopefully it's fairly straightforward. After the break, which I'm going to ask you to come back by 22. Oh, is that too long? Don't shake your head at me. What do you reckon? 22? Okay, if you make it back here by 22, we'll be looking at something called B-splines, which is how we can join lots of Bezier curves together into one curve.